Neutrons have a wide range of wavelengths, from 0.05 angstrom till 20. That depends on how we thermalize the neutrons. So neutrons from the source are passing through different pieces of equipment. Some are at liquid hydrogen temperature, some others at 300 Kelvin, others at 2000 degrees. So neutrons, when going through this special piece of equipment, thermalize at the temperature of this thermalizer. And when they leave with the energy corresponding to that temperature. So that's why their wavelength can be so different. But that is very good, because then we can, sorry, this is order. We can study problems with distances at atomic, molecular, or biological scales. So we can measure or make experiments to detect features at the crystallographic scale, subcrystallographic scale in some cases, or bigger, like nanomagnetic particles, the nanoscale, cells, proteins, biological features, many liposomes, things like that, big, huge. With neutrons it's possible, but they have to be very, very, very cold neutrons. Cold neutrons. At the same time, we can have a wide range of energies, from milli-electron volts to electron volts. So that permits to study problems related to tunneling, rotations, vibrations, electronic transitions, diffusion. We can magnon dispersion, magnonic states in magnetic lattices, and so on. Neutrons carry magnetic moment, so then they interact with dipolar magnetic interaction with unpaired electrons. So we can study magnetic structures, elemental magnetic excitations, the magnon, I was telling you. I explained, I think, the first day we went to magnons. Okay. We can measure simultaneously magnetic and nuclear structures. This is the magnon dispersion relation of a compound. This is magnetic structure and crystallographic structure. So we can have different lattices, and the magnetic lattices are much richer than crystallographic lattices because they are in addition to crystallographic lattices. And the possibilities of the magnetic moment, of orientation of magnetic moment, are far more complex, richer, whatever you want to call it. So we have a ferromagnet, antiferromagnet, ferrimagnets, where the A and B unit cell do not compensate each other in magnetic moment. But then we can have this kind of sinusoidal magnetic ordering, or this kind of helical magnetic ordering. Fun, so moments are moving this way, according to along the crystallographic, the nuclear lattice. They are oriented, just moving in a plane, like a fan. Okay. Maybe triangular lattices, canted. The diversity is immense. So it is like a crystallographic lattice, but with magnetic moments, and neutrons can see them. Let's spend some few slides going into a bit deeper into what we are actually measuring. When we want to make a neutron experiment, in principle, somebody can joke and say, well, a neutron experiment, that is very easy. You only have to know how to count. And it's true. You only have to know how to count. You count neutrons, the scattering neutrons. You count them. You keep records of angles, energy, and something, but you are just counting. It is important to attend to the double scattering cross-section, which is the number of, this is the differential double scattering cross-section, is the number of scattered neutrons in this solid angle per second in a solid angle delta omega in the direction given by theta phi with a final energy between E and E plus delta E. So here you count any electron. You put your counter here in this delta S or ds, and whatever arrives there is okay, is good. Except if the energy is huge, or but in a energy window, everything counts. And that is the double scattering cross-section. If you integrate to the energy, or if you filter the energy, only energy of a given value, and no is accounted for, then you get the scattering cross-section, not double, scattering cross-section. In problems, in phenomena, where the interaction is elastic, there is no difference in energy. So the scattered neutrons have the same energy as the incident neutrons. These are the phenomena related to crystallography. So in a determination of a nuclear or magnetic structure, we only care with elastic scattering. That is called diffraction. You know it very well.